Good morning. Today's webinar, it's September 2021. This is Jason Lillywhite. I'm with GoldSim Technology Group, and today I'll be talking about finding and debugging mass balance errors in your GoldSim model that is simulating a dynamic system of flows and storage objects. And to start off, first thing I want to do is, first of all, just introduce the subject. In that being a mass balance. What is mass balance? It's a balance of all of your inflows, outflows, and changes of storage within a confined, some sort of system that you're modeling, in which there might be some, and when I say inflows, I'm talking about flows coming into the system from outside of it. So imagine you draw a boundary around your system. Any flows that come into that, be it precipitation or offsite drainage or whatever it is, that's an inflow. Outflows are things like evaporation or seepage into the groundwater in which you're not modeling the groundwater, any type of flow in and out through your boundary of your system. And then also the changes of storage within the system. Accounting for those things using the equation below, in which we integrate over time the inflows and outflows, and then subtract from that the change of storage, which is going always to be the initial volume at the beginning of the simulation minus the current volume. That equation should approximate zero, should be close to zero. And so that would be mass balance if you are able to get that value close to zero. And when I say close to zero, I mean there will be some probably some numerical errors due to the floating point numbers that we get some errors in your program, but they should always be very small. And I'll show you an example to see what those numbers might be. Okay, so why do we do this in a model? First and foremost, of course, to ensure that the model itself is correctly accounting for the total mass in the system. And then also to be able to demonstrate to your audience that, hey, this model, it does account for everything correctly. Even if the model was doing it correctly and you didn't show or demonstrate that, it could, it would not build confidence in your audience to know that it's working correctly. So being able to demonstrate it helps a lot. Before we get going into the presentation, I have a poll that I wanted to send out just to see where everybody's at. So I've got 3 different questions that I will launch here. You should see them somewhere on your screen, probably in the dashboard. If you don't mind, just take a moment to answer these questions. Once we get most everybody answering them, I'll move to the next one. I appreciate your time doing this. It's helpful for us. Okay, so we're about 65% say they want to incorporate mass balance into an existing model, 35% into a new model. Pretty much on par with what was answered in the previous session of this webinar. Okay, the next one. You should see the next poll coming up. Oh, I forgot to press launch. Okay, now you should see the poll. Well, the results are a bit different than the previous session, and today a bit more have been answering that you've never used mass balance before in a model. About half of you answered that way. 15% said you plan to use it. 20% you've used it at least once, 20% not very, or I'm very familiar with it. Thanks. Okay, last one. Okay, this one's split pretty much evenly between all three of them. A little bit different from the previous session. Previously, people were voting mostly that it's been challenging in the past, but today you've all about 33% for all three of those answers. Great. Thank you very much for answering that. That's helpful for us. Okay, so the agenda today, we're going to, I have the presentation split up into two sections. The first one being strategies to help you with existing models, knowing that while there are certain design ideas for a new model to help a lot with, well, organizing the model in a certain way to facilitate and much easier and cleaner accounting of mass. If you're coming at an existing model, it could be quite time consuming to reorganize a model at that point. And so you could be in a situation where you just need to figure out, or you just need to build an accounting um, functionality in your model, and perhaps you're finding that you can't, for whatever reason, can't get it to close, get mass balance to close, and you need to figure out where the problem is coming from. And so that's what this first section will talk about. The latter part of the presentation will talk about if you're starting from scratch, or if you have the time to restructure the model, what are some ideas that would help you in that case? All right. So as you've probably seen, those of you who have dealt with mass balance modeling for your system, that it can be, if you're coming at it from, here's an existing model, now I need to go back and I need to just do an accounting of it, you may have found that it could be like trying to find a needle in a haystack, trying to find where is this error coming from. You know, I'm doing the correct equation. I think I'm grabbing all of the inflows and the outflows that I have. For some reason, it's still not balancing out what's going on. So the point of this presentation will be to help guide you, provide some pointers and tips to find those errors. Okay. So mass balance accounting can be easily done as far as just the equations go, can be easily done with some expressions and some integrators. We have a model in our library that all you have to do is copy and paste this into your model, and it provides kind of the framework and then also some logging and error messaging along with it that is kind of nice, so you don't have to rebuild it again. And that can be found if you go to our Help Center in GoldSim. From our GoldSim website, go to our Help Center, and then go to, when you're in there, go to Model Library and Water Management, the Water Management section. And we've started, so it's up here at the top. Check for mass balance. So you just click on that, and you can scroll down and download the model. Okay, so imagine in your model, what you would do is you would draw an imaginary boundary around your system, and then you would determine what inflows are crossing that line and what outflows are crossing it, and account for those. Put them into the sum element called inflows and outflows. GoldSim will integrate those over time, and then you will also link the initial volumes of all of your storage elements, and then also link to your current volume. Those being subtracted from each other will be the change in volume over the course of the simulation. And then you do the equation of inflow minus outflow minus change in volume, and you should get approximately 0. Here's an example, here's an example plot in black, this black line showing the results of that equation called MB for mass balance over time. And you can see that the values on the left y-axis are showing very small numbers. That's what we're looking for. It's going to be somewhere in that range. 10 times, some number 1 times 10 to the negative between 12 and 17, something like that. Very small numbers, and that would be correct accounting of mass balance in that case. One thing to keep in mind, by the way, when I'm talking about storage in your system, it can come from the obvious places, such as a pond that you're modeling, tailings facility, something like that. But also it can come from delay elements. If you have a material delay, for example, in which you have water that it delays and maybe is even dispersed over time. To do that, to do a delay, it requires that a flow on the current time step is held in transit before it comes out the other end, right? So that is also storage. You need to account for those as well. Sometimes people forget about that. We'll talk more about that later. Okay, what I want to talk about now is how when you look at the plot of the mass balance, and what I'm going to do is now open a GoldSim model here, and I'll do a run, and then I'll show the plot. I should turn off my notifications. Everybody's trying to get a hold of me. Okay, so what you see here is in the black, you'll see that there is very small numbers here, and so we have balance. Now, what happens if I artificially go in here and I, for example, I don't know, remove one of the initial volumes? So right now I'm accounting for the initial volumes for all the ponds, and I'm just going to multiply one of them by 0, so that goes away, and now rerun the model, and we're getting some messages that are telling us that we have mass balance error. That's fine. And then I open the plot, and what we see is a constant. This black line is now constant, and it's at a pretty large number here, negative 24.7. And so what that tells us is that if you have a straight line, just a constant like this, that's telling us that we are not accounting for, or if it's a positive number, double accounting for some initial volume. Okay, so I'm going to now talk about the shape of that line, that mass balance line, the different kinds of shapes and what they might mean. All right, so a constant error like this one, it means that we're missing a reference to an initial quantity, but I should also note that would be, I should say, negative, and then it could be double accounting or over accounting, and that would mean it's positive. If you've accounted for one or more initial volumes more than one time. The reason this might seem like, oh, well, that's obvious. Why would I over account? Why would I miss one of those? This is so obvious. However, in a lot of real models, you have many storage elements. You have a long list of them, and so it can get easier to miss some of these things. If your line is cumulative and steadily rising with no drops, just steadily rising, like you see in this image, what that means is that you are missing you're missing an outflow, or it could mean that you are accounting for an inflow more than once. Likewise, if it's decreasing in a similar fashion, but just going down, then it's the opposite. You're missing an inflow somewhere, or you're over accounting for some outflow. If the line is moving up and down with what appears to be some sort of bound, and it may not hit 0 because you could have a combination of things that are gone wrong, but with just missing a storage element, and this could be a mass storage, or sorry, it could be a storage from a delay or storage from a pond. If you're missing a reference to any storage elements in your model, um, and and this storage element that you're modeling has an upper or lower bound, then you will see something like this where it's hitting what appears to be a similar point each time at the top or at the bottom, and it's going up and down like a pond would as it's draining and filling. If you have a sudden drop or a sudden increase, then you're missing a discrete change that you might be adding or subtracting from one of your storage elements. Okay, so now to the more possibly more likely situation, you might be having a combination of things that are missing or over accounted for. So using the clues that we saw before in some of those previous graphs, um, if you have a situation where it is trending upward or trending downward, like we see in this plot on the left, but also moving up and down as it goes, then that would tell you that you've got a combination of over accounting inflows or missing an outflow in combination with not accounting for some storage element um, in there. And then also, if you have something that does seem to somewhat trend, but is kind of moving up and down with not any real bound to it, um, then it could be that you have a combination of inflow and outflow that's not accounted for. The combination of those two things could cause a line that's moving what appears to be somewhat randomly through time, but a large number. Okay, so these are not going to answer every single question that you might have that you might run into, but knowing just the basics of basically what the shape might look like, depending on um, uh, the type of system that you have. This kind of these kind of clues can help quite a bit in pointing you to the right direction. But that's not the end of it. There are more things that we can do to point you to where the problem might be occurring. So the next idea is to divide and conquer. So initially I've been talking about drawing a boundary around the entire system, and that's what's represented in this blue line, which we account for flows going into the system that we're modeling, in this case, a simple example model that I'll be showing you here. Draw a line all the way around it, and you'll be accounting for flows that come in from the upstream, maybe some precipitation, maybe downstream flows are leaving the system, water's being consumed at maybe some demand points, and that would be leaving the system. So that's the overall boundary, but it's also useful to do mini or regional mass balances, smaller ones for segments, certain segments of your system. So for example, if you draw this red line around just these three elements, then that would be, a smaller subset of the main, and then you would have to redo the accounting for this subset in which the flows that are coming in are the flows crossing this smaller red boundary instead of the larger one. So we might consider the flow that's coming from this pond over to this one, this pumped flow. That would be an inflow to the system. The outflow would be this line here leaving, and then any other evaporation, consumed water that's not shown here would be accounted for. By doing this and then repeating this process throughout the model and creating multiple kind of regional or smaller mass balances, then if we hit an error, because it's being done at this smaller scale, then it can point us to the location of where the problem is occurring. Okay, the next strategy is using some logging and messaging. And like I said, this comes with the model that's in our library, and it's using a GoldSim script element. Within the script element, you have the ability to show messages in three different ways. One way is not very in your face. It's just writing a message to the run log. So the simulation will complete, won't show you any errors during the model. When it's complete, then it will write a message to the run log that you can go open. It will tell you that, oh, hey, by the way, there's a warning written to the run log, when it's done simulating. So then you can go look at it. That's one way to show a message that you've got some issue. Another way is where it would interrupt the model when an error occurs, and then it will go ahead and just tell you with a little window, like the one shown here on the left. It'll say, hey, you've got a mass balance error of blah, 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 starting on whatever date. And the nice thing about a script element is that you can insert outputs of elements within the message. So you do that with a curly brace and an equal sign, and then you put whatever expression inside of there to output the value that you want to see. And in the case that we're looking at here, it's a little bit different on the right, a little bit different unit, but same idea. Anything that any expression that you put in the curly braces in there will evaluate to SI units. So that would be meters. I think grams is SI, and seconds. So if you want to show an output, like for example in this one on the left, in gallons, then you would have to use what's called casting of units off in the expression. And you would want to cast off gallon units so that it would do a conversion from cubic meters to gallons. And then once that number is ready, then on the outside of the curly braces, you would just put the word gallons. That's what I did. And so just keep that in mind. Everything's SI units. Everything evaluates to SI units in a script message. So to do a conversion, you have to kind of do this trick where you cast the unit off for that particular unit that you're interested in. And GoldSim will do the conversion for you when it casts the unit off, which is kind of nice. Also, in GoldSim 14, which will be released shortly next month, October, our October webinar, Rick will be introducing the new features in GoldSim 14. I will just out of necessity be telling you about a couple of them. One of those is that we have some new date functions in which you can, from any date output in your model, you can extract from that the month, day, year, or you can build a date by inputting month, day, year, and it will then output a date value. So that's kind of nice. Makes it a little bit easier to work with dates. That's kind of a minor feature in 14. There are other ones that are bigger than that, but that's useful for telling you exactly when, for example, in this case, telling you exactly when something's happening. However, I will say that in this particular case, the way that this mass balance works is that it shows you this message will appear at the date that it occurs anyway. So the date would actually be shown down in the bottom of your GoldSim model anyway. But just in case you happen to, maybe you want to delay your messaging to the end of the simulation or whatever case like that, then that could work as well, showing the date there. Okay, another tool that you can use in addition to reporting and logging is interrupting the model and allowing you to walk around into the model and view all of the outputs available. This idea brings up a couple of kind of high level and complicated, not complicated, kind of a advanced GoldSim concepts. So get ready for something that's a little bit more advanced here. We're going to talk about the causality sequence in GoldSim, and the best way for me to do that is to show you the model itself. So I'm going back into this model, and let me go to the top level. Here's the top level of this model. If I browse into the system, this is the similar to the picture I was showing you before, where we've got a stream, a diversion structure. Water's diverted from the stream, goes into some ponds. There's some recycle, water moving from one pond to another and then back again. And then we've got some demand. Some of the water is returned back again to the system. So you can see right here, we've already got at least 2 flow loops. One flow loop is over here, and another flow loop is over here. In addition to flow loops, we also have feedback loops, feedback of information. And I'm going to be talking about this quite a bit. I don't want to get into it right now, but just want to show you that this is the model we're simulating. And if I go up one level, then we see we have mass balance check here. So if we wanted to interrupt the model when a mass balance error occurs, we can use an interrupt element. And for those of you that are new to the interrupt element, when I open it up, you'll see that essentially you just trigger it. You tell it when to interrupt. And so the nice thing about the mass balance model that you'll find on our website is that it uses a milestone element, which can tell us exactly the date, the elapsed time, or the status. It becomes true when this milestone is triggered. And this milestone happens to be triggered when the very first mass balance error occurs during the simulation. So we then just point that over to trigger our interrupt element. And the interrupt element says, at the time, at exactly the E time that we have the E time output from the milestone telling us the exact of E time of the milestone. If those two things equal, that's going to be at the elapsed time which the error occurs, but then also make sure to check that the completion status is true. So if it hasn't triggered, then don't interrupt, but only if it becomes true. When it becomes true at exactly that point in time, then go ahead and interrupt the model. Okay, so if we have a situation where there's a mass balance error, this will trigger and interrupt and pause the model, and then we can go around and browse the model and see outputs as they are at the exact moment in time in which this error occurs. There's a chance that when you add a new interrupt element, that it does not end up at the end of the sequence of calculations. So now we need to talk about the causality sequence, and that you can view by going up here to Model and then Causality Sequence. And you can see the whole list of all the functions in this model, and you see that the interrupt is down here toward the end, and that's where we want it. This represents the order in which calculations are done on every time step. So at time 0, these calculations are done in this order. Next time step, all in this order. And if it turns out if your interrupt is not near the end, if it's not after these other elements, then when it interrupts at exactly that moment in time, then the following elements that have higher numbers than 52 in this list will still be referencing the value from the previous update. So it's important that you have this element at the end if you're going to be viewing the values when it's paused of these elements. So you'll want to change the precedent. And to do that, by default, every element has no changed precedence. It has its own place. GoldSim tries to figure out on its own what the order of all these equations are based on how you've set the model up. So it will set everything in order for you. However, this element, because we want it to report to us the outputs of all the elements in the model, we want it at the end. So a good way to force this element to go to the end is to essentially, first thing is to just open up your causality sequence. So model causality sequence, and then just go down the list and see what's at the end. And then just say, well, I want to make sure that it goes after, at least after this element, whatever that element that is. It turns out this is already at the end, but there's a good chance it won't be in your case, right? So, so what you want to do is highlight the element right-click and select Specify Precedent, and then go find the element that you found in the list. Make sure that that you specify that element as a precedent to this one, and then that will force this element to be after the one that you select. After doing that, when your model interrupts, then the other elements that you want to see their outputs of will already have been updated prior to the point at which this is updated. So I realize this is a bit of an advanced topic, but definitely very useful, helpful, definitely helpful, because if in the case of which this interrupt is not last, let's say it happens near the beginning of your causality sequence, well, that means everything you go and hover over will not be up to date. One thing yeah, I guess I probably don't need to demonstrate how that works, but just keep that in mind as you're building the model. Okay, finally, one more thing. And I mentioned this in many webinars, the point about high resolution time history results. So if you have a model that is allowing unscheduled updates, like in the case that we see here, where if you go to the advanced time settings of your model, then you'll see the box checked. And just to remind you where that is, go to simulation settings here, then go to advanced here. This box right here, allow unscheduled updates. If this is checked, then in addition to the time points that you specify, which in my case is every day, every 1 day at midnight, every day at midnight, it will update all the calculations. Well, if you have this box checked, there could be times when there's an additional time step in between the days at midnight. Okay, so with that, then what we need to know is, are we accounting for everything in the unscheduled updates? And so to understand that, to see that, then you would want to temporarily check this box that says include unscheduled updates. That way, if you were to try to debug your model and look to see what's happening, where am I missing flows? What am I missing here? If you check this box, then you will see everything in the time history result and have a better understanding of what's going on. This is really good for debugging. I would suggest unchecking this after you have finished debugging the model and you're ready to move it into production mode. Definitely uncheck that. Okay, so here's an example plot on the right showing the difference between when you're showing high resolution results versus not. When you're showing high resolution results, you'll see inserted points that may be occurring that you don't see on a regular plot. And these could be key when you're trying to figure out why you don't have mass balance all the time in some cases. For example, a very common one is where you have an overflow occurring on one of your ponds, but you didn't realize it. Maybe you didn't even account for it because you weren't expecting your pond to overflow and you have an upper bound on your pond. Maybe you have some logic in the model that tries to always keep the pond from getting to the top of the spillway or something. Well, maybe something happens in an unscheduled event and it overflows for just a few minutes and then comes back down. You may not even see that in your regular time history plot of the pond. And you'd miss it and you'd wonder, well, why in the world are we not getting mass balance? I've got some sort of loss occurring at some point, don't know where it's coming from. If you enable your unscheduled updates, and then you would see, oh, there's a little spike that occurs for a few minutes. It must be, an overflow occurring. The way that it would appear if you have a very short term overflow that you're not accounting for, you would get a plot that looks like this, but it would only be jumping just one time. It wouldn't be continuously going up, but you would see it all of a sudden jump a little and then stay flat. And so keep an eye out for that. If you have multiple overflow times and it's not being accounted for, then you would see jumps in an accumulative fashion in this way. Okay, the next subject is organizing the model. The concepts that I'll be talking about here are somewhat similar to what we have in our style guide, and also borrowed from some of our advanced users that have given presentations. In fact, some of these concepts were demonstrated by some of our advanced users at our last user conference um, held in Seattle in, gosh, when was that? 2018, I think, maybe 2017, when we held our last user conference. And by the way, we would like to have another user conference once once we're at a point where we can start thinking about that kind of stuff again. Hopefully, hopefully sooner rather than later. All right, so model organization. I'm going to talk about a few things, mainly just having to do with organizing the model well. It goes a really long way. Staying organized is the key. It really is. And you can use whatever methods that you find easy for you to use. What I'm showing you is somewhat of a preference, but definitely tried and true. I started building models as a consultant in 2006 and worked with various models um, for quite a few years in GoldSim, and found that many of these ideas worked well for me. And I have seen them since while working at GoldSim for the last 11 years. I've seen quite a few models and I heard from quite a few people that some of these ideas work well. So the first thing I want to talk about is highlighting inflows and outflows. And to just give you a little bit of background, what I'm talking about here is if I go to this example model where we see the system of flows here, I'm talking about if you go into any of these components, my preference is that you hold to kind of a standard setup within each one in which you highlight the flows that are coming in and the flows that are leaving. Just highlight them so that when they open it up, it's obvious where the inflows and outflows are. So I just went into one of the pond containers, and you can see I have highlighted green the inflows that are coming in. You also can tell that they are inflows because the input port is highlighted. The input port is shown here on the left. It has a dot. This is since GoldSim, I think 10.5, we've been having these. But in the view menu up here, you can change the way that the ports appear. The default is called the Smart View, in which it only shows ports that have exposed inputs or outputs, where there's this dot. If you hover your mouse, you can see the port appears so that you can click on it. That's why it appears. But you can force all the ports to appear. If you select all, then all the ports appear. And you can make them all turn off if you wish. But for what we feel is that it's best to have it on this default because it actually provides you some good information. Just by glancing at this model, we can already see that we have information coming from outside into these elements located at the top of the screen. And we have outputs leaving this container in these elements down here on the right and at the bottom. So what I wanted to point out is that I have highlighted green inflows and highlighted blue outflows. And I just hold to that color code for all the containers. And just keep in mind the way that you change these highlight colors is to right click on the element and go to Appearance, and then go to Fill, and then change it from transparent to some color. In GoldSim 14, we have a new color palette. And we also have a way to select a color with a little dropper thing. And once you pick a color, you can easily add it to a custom palette that can be saved with the model and exported as XML. So this is kind of a nice thing, off subject, but I just wanted to make sure you understood that, because currently in the current GoldSim, saving a custom color palette is a little bit more involved. So this makes it a lot easier to deal with colors, especially when you're working with a team and you want to ensure that everybody's drawing from the same potentially custom color palette that you might have for your project. Okay, so in addition to inflows and outflows, there's also feedback information. I'll talk about that in a second. So yeah, I already talked about the separating the inflows and the outflows there. Okay, the next thing that's really important to do is to separate an outflow request from the derived or from the calculated outflow. So let me go back to the model to describe that. Here is a pool element, and as you probably know, the pool element allows you to define its bounds, its inflows, and its outflows. So in this particular case, I have two outflows defined, one that's driven by evaporation and another that's driven by feedback coming from pond 2. That's just saying, okay, pond 2 is running low. We need to send it some water. How much are we going to send it? Well, we've got this pump sitting here. It's got some capacity. We're going to try to give it everything we can. Whenever it asks for water, we're going to try everything we can to get water over there as a second priority to evaporation. That's what this is doing. So both of these, no, I shouldn't say that. The first one, evaporation. Evaporation is a function of the volume in the pond, right? It's actually, immediately it's a function of the surface area, the water surface area of the pond, but that is ultimately a function of its volume, because we have a volume to area relationship table that we're using to calculate what the water surface area is on this pond. But anyway, just know that when we calculate evaporation rates, it's a function of the volume. So this request in this table right here, this equation, the request in this particular case would for all intents and purposes, be exactly the same as the calculated outflow of the evaporation rate. They're going to be the same because it's a function of the volume. But even if that's the case, I would say, just to keep everything simple and straightforward, I would say still don't refer to the request in other places as if it's the outflow coming out. It just confuses things. It is much better to always separate your requests from your outflows as two separate entities. If I need to refer to how much water is leaving this pond due to evaporation, I would always do it, always do it as the defined outflow that you find in the output port of this element here. This is the resulting outflow. And so what I do is I add another expression that simply refers to that particular output, which is the pool dot evaporation. So I do that for all of the outflows, including the overflow. And now, as you can see, I have zero interaction with this pool from the outside. I have essentially isolated it with my interface. And that's really what this is. These colored elements around here represent the interface on the pond. We have things coming in and we have things going out. Okay, so now it's time to talk about references and feedback information. In the model that we're looking at here, I've got these two things in this pinkish red color here. I use that color to refer to information, and I propose that in many of these kinds of water balance models, that if you can move the references like this to information, as opposed to the flow references. If you can move references to information, these are things like, hey, this pond over here is running low, or I've got this demand for um, dust control over here, and I'm trying to ask for water, make a request from another place. Those kinds of things, equally important to be linking them, but they do not represent water moving. They represent information exchange. And when you look at your system, if you include the information exchange in this system, it very quickly in a real model will clutter this view. And so let me give you an example. If I go back into this pond, we have this incoming information that says pond 2 is low. That's the other pond, right? It's just telling us that it's low. It's run low. Well, I could refer directly to that other pond to get this information because that's where it's at. That's where we find out if it's low or not, in that other pond. So if I go back up one level and I go into pond 2, you'll see that there's this output called pond 2 is low. It's just a status element that once a water level drops below a certain target, it becomes true and says, hey, we're low. We need more water, right? I could just refer directly to that output over there and bring it into this pond 1. So let me just go ahead and do that. I'll just change this reference to then refer to pond 2, the status element. Okay, so I just made that update. If I go up a level, you'll see there's a new line here. And it's green because it's a Boolean it's a conditional output, not a value. So with that, then you might say, well, it's not that bad. It's a different color. It's, it just makes sense. We've got water going this direction, and then we've got some communication of information going the other direction. No big deal. Well, in a lot of cases, that's fine for a very simple system like this. But once you get more complicated, which most models do, then this becomes critical, and you start to lose the message that you're trying to portray with GoldSim in this container, in this system view. What we really want to see here is a schematic of where the water's moving. And so what I propose is that you move references like this up one level outside of this container and then bring them back down so that we can hold all the information references in one place and then bring them back. By doing this, it greatly simplifies the view of the flows, which is critical to accounting for a mass balance. Because if I'm looking at this right now and I see that all the flows are showing links going to various places here without the information cluttering it, then it gives me a much better picture of where the flows are and if I'm accounting for everything correctly. So for example, when I told you about how I drew a circle around this part of the the model, let's say I want to do a mass balance of just this part. Well, if I have this reference, this information reference going out here, it might at first make me feel like, well, there's an outflow going over here. And that's not an outflow, right? That's information. So now I'm going to go back here and refer back to the information that's coming from the higher level. So I have this folder called System References, and that's where I just put all of these outgoing information references is in that container. So pond 2 is low. That's what we're looking for. All right, so then I go back up, and now we can see if I draw a circle around this and I want to do a mini mass balance around just this region, then I can already see immediately that there is some outflow going in and coming out right here. And there is nothing else going back up to pond 1. So it's very helpful. And here's another way to view how we move information references out of the system model. So we were just looking at pond 1. Here's a screen capture of the browser view of the same model. What we do is we say, let's move, well, this isn't actually looking at the same output, but it's the same concept. I want to refer to the volume of pond 1 over in pond 3. So to do that, I add a reference up here, up a level in the system references called pond1 volume, and I refer to it. So that's this link here. It's going up. It's not going to a sibling container. It's going to a parent container. Well, it's actually not truly a parent. It's, I guess, an uncle or an aunt container. It's over next to it. But then over in the other pond, pond 3, if we want to refer to that volume, instead of referring to it directly, we're just going back down with a reference back into that pond. And so what you end up with at the upper level is this feedback view up here from system references over to the system model. Okay, so by organizing the model this way, it makes it much more clear when you're trying to do an accounting of all the flows and where they're going. Okay, so I also separate and highlight the references to information separately. So incoming information I put up here somewhere by the inflows, and then outgoing information I put it somewhere further away down, maybe by outflows, inflows and outflows. So we have incoming information, we have incoming flows, we have outflows and outgoing information. So the pink highlighted elements, you should be able to find a reference in your higher level container called information references that has those. Okay, so this might seem like doing a lot of work just to get things to view the way you want to view it, but what you'll find is that if you build a model this way, it might seem a little bit like overkill at first, but in the end, it pays off tremendously. That's what I've found. Okay, the next thing that pays off is when you have input data, just static input data. This can be in the form of a scalar, vector matrix, lookup table, time series, that kind of information in your model. That's just static information, not expressions, just the static information. Well, a time series isn't technically static, but it's just a data input, right? Anything like that, if it's being referenced in multiple places in your system, then it's a good idea to clone it. So here's how that works. If I go into the model and I go to input data, you'll see that the input data here is not being referenced in the system model. Well, that's because I've cloned it into there. And the main reason I do that is because some of these things are being used in multiple places. So let me see if I can find one that's being used in multiple places. It would have in the clones tab, so you can see all of these elements are cloned. Well, not all of them, but most are cloned. They have a little clone symbol on the top right indicating that they have that. And if you open up the properties, then you'll see there's a clone tab. And in there, then you can see where it's being used. And I'm just trying to see if I have any that are, here's one that's being used in 2 places. So this one's being used, this is the water demand for one of the users. It's being used both at the demand point, probably just for reference, but where it actually matters is over at pond 2, because that's where we're making the request to get that water. And so if you clone it to both of those locations, then that would remove the need to have a link, and I mean an influence line from pond 2 to B. So let me go in and show you. Well, you can also, if you go to the clones tab, you can just double click on one of these items and it will take you there. Okay, so here I am. I'm inside it. It's this, I'm referring to this as city B. If I go up a level, you'll see it's this container here with A and B. These are 2 water demands. If I go back in here, so city B has this water demand, and I'm just referring to it so that I can calculate a shortage if we have a shortage, if we're not able to supply all the water. So it's not critical to the calculating of flows necessarily in this particular case, but it's being used as reference to calculate a result in the model that we're looking for, which is are we short on water? So it's just a reference, but you could imagine that if you had this just embedded in here, then you wanted to come back up a level and go into pond 2 and also refer to the demand, because this demand is being used to drive an outflow from this pool. There's this demand B right here being used, and that's over here in this container right here, demand B. So you can see it's cloned. And so because it's cloned, it's going to always have the same value. If I change the value here, it will change the value in all of its clones. So it's just replicated, but it does not produce unnecessary communication lines between B and pond 2 by having this cloned, if that makes sense. Okay, we're getting a little bit low on time, so I'm just going to mention a couple of more things, mainly related to the complexity of your model when doing mass balance. Okay, there's another approach completely different from all of this, that in which we can do the mass balance externally. There's definitely some pros and cons here, and I just want to talk about it a little bit in case you want to consider doing that. So this model that we've been looking at all along has a mass balance built into GoldSim, which is great because it's all easy to work with. However, it also requires that you build a whole bunch of references from the system. So if I double click on the line that goes from the system to the mass balance, you'll see all of these references being put in here, tons of references coming in. And that over a large model can become quite a bit. And it also kind of could be a little bit of a distraction. For example, let me see if I can find one. Let's go to this one right here. That's called outflows input 2. This is coming from water supply to outflows. Okay, so if I go there, then we see we have this output port. It's going somewhere. It's actually going to the mass balance check, this output. That's the only place it's going. And so if you're looking at this and saying, well, this must be feeding another place in the model, I need to know where that's going. Well, it's just going for an accounting purposes. It's not really going to, feed anything else. So that would be important to know, and it's not exactly clear at the moment where this is going, unless we right click and go to effects and we see where that it's going into this outflow of the mass balance check. Okay, so what can we do to even more simplify this model even more to remove the references to a mass balance check? Well, we could just use a time history result, include all of the inflows, outflows, changes in storage, and send that out to Excel and do the equation there. So let me open up that example model. So here's the same model, except the mass balance is really just this time history. It turns out that it's kind of easy to just sum up all of your initial volumes if you want. You don't have to do it that way, but you can also integrate all of your inflows and outflows if you want to make it a little bit easier. But you don't have to do any of that. You could just go ahead and reference all of your inflows and outflows. I just added this pool element so that I could find all the inflows from to the system and all of the outflows from the system. And then I just have to link that thing called system flows right here and send that out to Excel, including all the references to the various ponds and the material delays. And then if you export all of those to Excel, then what you end up with is this. So everything from column A through G is coming from that time history result. So we have our inflows minus outflows here. We have our storage elements here. We have our material delays here. And then we just simply subtract the two, inflows and outflows, subtract them from the change in storage, which is all of these. And then you get mass balance here, just subtracting these two. from each other. And so you could do other things, like you could highlight if there's ever a mass balance error in here anywhere, um, and you could even report mass balance errors back to GoldSim on subsequent runs if you wanted to. But um, it's pretty simple just to do any kind of thing like that in Excel and provide this as a report. I tend to for a more complicated model, I would tend to lean toward this approach, just because of the simplicity that it provides you in this model and allows you to just focus on the model of the system itself. Um, but the one thing that you just have to keep in mind as you're building models and working with them, making changes to them, is that if you ever do make a change in a flow and reroute a flow to some other place, that you have to make sure you account for that um, in your mass balance check, mass balance calculations. But once that's taken care of, um, any other changes that don't involve rerouting of flows will automatically be accounted for in your mass balance check and make your life much easier. So that concludes the presentation. Thanks very much for participating and answering the poll questions. I'll wait around here a bit to see if you have any follow-up questions. But otherwise, if you don't have any, thanks for joining, and we hope to see you next month, where we will introduce to you GoldSim 14.0, and you should expect to see that version coming out before the the next webinar. Everything is on track currently, so it should be pretty soon. All right, thank you for joining, and like I said, I'll wait around here to see if there's questions.